So, I mean, one of the things I was just talking to Jeff about during the coffee break is why we're so worried about big data. I mean, in some sense, I think in a really deep sense, the reason why we acquire data is to build better inferences and build a better understanding of the universe. And so more data should be considered a good thing. And I think the reason why many of us are worried about it in so many different ways and express that in conferences like this is in part because it means that the ways in which we've been working will have to change in something fundamental or maybe something on the periphery, but it will have to change. And so if the purpose of data is to facilitate action and understanding, this concept of machine learning is perhaps too small in a sense that learning is a pretty kind of inward-facing, it's a sort of solipsistic exercise where just kind of knowing something doesn't mean you're able to do anything with it. And so we're stuck with that term, but I want to sort of emphasize the fact that when we're teaching machines to sort of figure something out, we're doing it because we want them to be able to help us do prediction, and we want to have them help us make sort of maximal use of our resources and put sort of the learning into practice. So just to sort of get everyone onto the same page, what is machine learning? It's a form of artificial intelligence. It's a set of algorithms and analysis frameworks that can be used for making predictions on existing data, but as you'll see throughout most of this talk, I'm mostly interested in making predictions on new data. And in many ways, it goes back to high school or college statistics in basically just giving us a better way of doing classification or regression or clustering. But they have some wonderful properties in being able to learn from existing data and give back results which are calibratable and something that we can actually inspect and understand where they came from. Machine learning today is widely used, obviously, in industry. It's becoming more and more used in industries like our own. And what it's typically thought of as being very good for is with high-dimensional data. That is dozens or hundreds or thousands or even million-dimension data sets. Huge volumes, obviously, and interestingly, heterogeneous data sources. So when you're dealing with columns of your data that are of a different type, words and floats and things, this can be quite useful. And then in the context of time domain, obviously, it can be quite helpful if you're able to do this at scale with large rates coming through your system. Interestingly, some classes of machine learning algorithms and approaches are actually very parallelizable. Generally, the linear algorithms are ones that can be sort of put into a MapReduce paradigm. But some of the best ones tend not to be. And so there is sort of a computational expense that we have to worry about. But one of the sort of main takeaway points that I hope you get today from my talk here is that I don't see the machine learning that we're capable now of doing with the machines that we now have access to in a basically commodity sense as being the kind of bottleneck for using machine learning on the types of data we'll be encountering, say, in the LSST era. I think there are other challenges, but I don't think this is a big data problem yet in astronomy in the context of using this as a new toolkit. I should say that machine learning's been around and used in astronomy for a number of years, actually over a decade. And usually that's put into practice in the context of doing photometric redshifts or doing star-galaxy separation. And almost always, up until the last few years, has been done in the context of essentially the static sky universe. But those that know me know that I'm interested in sort of all things that go bump in the night. There's the type 1a supernova and the type 2p supernova, the known knowns that we're looking for, and then there's the unknown unknowns. I'm sorry, people that don't like Donald Rumsfeld, but it's very useful here. And then the unknown unknowns, which by definition I can't even put up on this slide. One of the things to take away from the fact that we actually have a whole class of things that go bump in the night that we know to look for. We have things that we think we should be looking for. And then we also, if we're going to be using these new toolkits, we want to make sure that we're able to find things that we hadn't even thought to look for before. The other thing I want you to take away from this slide is the time scale over which some of these events are changing. You notice that for the neutron-star merger case, which has a deep connection to the gravity wave universe, and is one of the things that I'm most excited about with LSST, for instance, these are changing on timescales of days. And if you think about discovery of these events in a very massive data set that's streaming through your system, you now want to be able to maximize your science by actually throwing big telescope resources at that location in the sky. And so going back after the fact a year later and say, oh boy, there was the first example of a potential emerging neutron star event in that part of the sky. I wish we had gotten to it, isn't very satisfying. And so there's this extra sort of urgency that comes in needing to gain inference on a time scale that's appropriate for the science that you want to do. It's not just because you want to publish this before the other guys. It's because to maximize the science that we do in the time domain, we typically need to marshal resources around. So in the big data challenge, I'll frame it this way, is really not so much at the algorithmic level, but it's in applying the right algorithms and frameworks to the streaming data so that we can minimize the amount of time that we spend on things that aren't that interesting and maximize the time we are spending on things that actually are interesting. And that's fundamentally a resource constraint. We already heard a lot about what LSST is expected to produce in the context of the time domain. Millions of supernovae a year is quite daunting to groups that have been basically having people look at all the data. There is something which obviously breaks at that moment. And then obviously just the tremendous onslaught from other observatories is certainly on the horizon. One of the, I think, important things to point out is that there are a number of surveys which have been going on in the time domain and are about to go on that will, in many ways, replicate the type of data that will be coming from LSST, if not the volume. At least we'll have a chance to sort of cut our teeth on something that we can actually now put into practice. But that's the fundamental question here, is how we do discovery, follow-up, and inference when the data rates and the requisite timescales for action on discoveries preclude human involvement. So one of the things that I've been spending basically the last decade of my life on is in working towards a sort of fully automated scientific stack in the context of time domain for transients. And if you sort of go from the bottom to the top, there's obviously subtleties here that I'm leaving out, but going from strategy of how you're going to observe the sky, to scheduling telescopes, to observing the sky, to pulling the data off the telescope and reducing it, to finding things and sticking it into your database, to discovering things, to classifying things, to following up, to typing those things after you followed up, to doing the inference. I think we've taken a big chunk out of all of this and shown that we've been able to put into practice the ability to do this without any people in the loop. And I want to just make sort of a bit of a fine distinction on the difference between discovery and finding. I mean, you normally think of that as the same thing. If I go over my LSST data and I have an object which appears to be new because it matched some sort of threshold and I stick it in my database, haven't I discovered it? Well, no, it turns out that just doing that, you wind up getting a lot of spurious stuff into your system. So discovery is really the moment when you recognize that this thing is actually important and you want to now follow through on that in some way. And in the context of imaging surveys, you might say that discovery is the recognition that this is astrophysically real and not some sort of bogus artifact of the system. Classic example of this we've seen throughout history. Galileo actually had Neptune in one of his logbooks and recognized it as a weird star. And so he moved on, so it took another 200 years for it to be actually discovered, even though in his database he had actually found it. He would have been pretty famous, I guess. So what I'll basically be talking about here is some work that we've been doing in the context of automating this stack. And the first paper is the one from the bottom, and that's where we were doing both discovery and classification using machine learning. And then a paper which just came out yesterday is basically doing better machine learning in the context of discovery. What is it? What do I mean by discovery here? And I'll focus basically on the discovery part, and then towards the end of the talk about how we're doing classification with machine learning. Really, the goal is to build a framework to discover variables and transients without people in the loop. And you notice there's a little collection at the top of bogus candidates. These are things in the database that are not astrophysically real, and things in the bottom that actually are real. And one of the things you notice is it's sort of, the things that are real basically all look the same, and the things that are bogus all look sort of bogus in their own way. It's like Anna Karenina, like, every unhappy family is unhappy in their own way. Well, anyway. The other sort of deeper goal, I think, than what I have in the box here is that we want to be able to do this really fast. And to do that fast, we need to have something which is parallelizable. But also, we want it to be transparent, so if I make a mistake, and we recognize that after the fact, I can go in and correct it. I can make this versionable, too. So I say, this part of my survey was discovered using these sets of algorithms, and then the next instance of the survey can be discovered something else. So it can always reproduce it. In the context of reproducible science, having a machine learning algorithm which is basically taking the place of what people used to do, I think is critical in all these different fronts. And this is critical also because for the Palomar Transient Factory survey where we did a lot of this work, we're talking about sort of 1,000 to 1 problem. 1,000 candidates in our database show up, and only one of them is actually astrophysically real. And so we're doing a massive needle in the haystack problem that we basically have to sort through. And just to give you a sense of numbers, there were 1 billion candidates in the Palomar Transient Factory database over its sort of 3-year lifetime. It just started up again in a new incarnation called IPTF, and that has already 100 million candidates just in the first couple of months. So, think about how we would have people look at all that. That'd be hard. Just like with people, however, discovery, even in the context of machine learning, is imperfect. It is not, this is definitely real or this is definitely not real. There are gray areas. But one of the things that we've learned over the years is that there are certain algorithms in machine learning that do better with these types of data sets. And one of the great things is we've been able to really kind of, sort of, again, cut our teeth on real data to try to figure out which are the ones that work. And the idea is that we would have all this kind of in place algorithmically and have all the best practices in place before LSST comes along. Just to give you a notion of what things look like, you take those postage stamps and you project them into lower dimensional space. In this case, we're doing sort of, basically it's a 42-dimensional space. And you see a couple of histograms of things that we know to be real and things that we know to be bogus from a trading set. And what we're trying to do is for a new candidate, figure out whether it's real or bogus. And what's great is that you really want to be sort of to the bottom left of this curve up here of misdetection rate and false positive rate. And some algorithms on the same data just do worse. This one that I've highlighted called random forest has a number of interesting properties, one of which is that naturally in building this algorithm, you wind up getting probabilities out of your classification, and whereas most of the other ones, pulling probabilities out is very ad hoc, but there's something natural that comes out of that. So in the context of doing inference and taking action on that inference, having probabilities come from your machine learning system is pretty important. And this has been put into practice in real time. I think one of the big highlights from this system is the discovery of the nearest type 1a supernova in about 30 years. It's called 2011 FE. And it was in the Pinwheel Galaxy. It got to be very bright. Some of you probably could see it with binoculars in a dark site. And what's important to note here is that we found it about 11 hours after what we now believe to be the explosion time. And it would have been found. This object, really hit you over the head. Amateurs love this galaxy. So it would have been a few days probably till it got bright enough for amateurs to start jumping up and down. But the point is, because it was found early, and because the machine learning algorithms basically promoted to the top of the list of something to be followed up, it got followed up within, I think it was about an hour of the data having been taken. Because of that, we were able to do some very interesting science. I mean, again, what is the purpose of doing all this? If, obviously Pretty Pictures are a great example, but it's really to do some novel science. So because we've been able to find this thing early, we're able to put very early limits from X-rays, from X-ray emission from this location, and also be able to continue to follow it up and watch the brightening in the optical regime and the color changes in the optical regime. And that allowed us basically to infer, and this is a bit of a busy slide, that everything in the colored regions are excluded in terms of effective temperature and average density of the thing that wound up exploding. And so this is really fairly strong evidence, because we ruled out all different types of main sequence stars, that there had to be a compact object involved in what wound up exploding. And you appeal to this without having to look at the spectra and without having to invoke theory. This is, there's a little bit of theory, but it's actually a pretty clean result, I think. So that could only happen because there was essentially a machine learning discovery engine which was looking at data in real time. So I'll shift gears a little bit. How am I doing on time? 11 minutes. Great. Into sort of this notion of automated classification. What I mean by this is, after we've realized that something is astrophysically real and we think it may be interesting, is to come up with a notion of what this thing is, so that we can decide whether we want to put it into the bucket of, give to our collaborators who work on something we don't care about, or take it for ourselves. And you guys are supposed to be laughing. I'm not really good at jokes today. Anyway, so we need to know what this thing is. It'd be great not to have to involve people in this part of the inference loop either. But there are considerable problems when we start getting into time series land. Data is noisy and it's irregularly sampled. We can have spurious data, that is, I'm pulling photometry of a real-world system, and I'm going to make mistakes sometimes and underestimate error bars. How do I know that these aren't sort of real fluctuations and I've just found a new type of event, right? This makes anomaly detection very difficult. And if I'm thinking about follow-up, the telltale signature of what it is following up this microlensing event, may not have happened yet, so I have to have some predictive model of where this thing is going in the context of the things that I know that I'm interested in. So how do we do this with machine learning? Well, because we have this sort of heterogeneous data and it's irregularly sampled, we basically take that data set and we engineer what are called features, and we put every single object and its light curve into this homogenized large dimensional space. We're now sort of at the hundreds of features level, and just computationally we're able to do a whole bunch of basically statistics on all this data very, very quickly, in sort of less than a second on commodity hardware. But what's also interesting is that we realized pretty early that if you've got one data point and you're trying to figure out what something is, context is pretty important. So now we think about, actually, when an event is found and we realize it may be interesting, we sort of explode a whole bunch of questions out into the web and ask everything we can of all the databases that are out there. But some of the databases may be down. Some of these surveys may not have looked in that part of the sky. So you need to build a learning system that's capable of dealing with missing data. But context is obviously very key when you don't have much data at all. In the time series sense, but once you wind up getting a lot of time series, then things become pretty interesting and you can learn a lot. I'll talk in the end just about how we're doing this in real time in sort of an online mode, but in an offline mode, you can imagine applying this to large surveys and time domain surveys. And what you really want to do is sort of take a whole bunch of streams of time series data and classify every object into its appropriate bin in this large sort of taxonometric tree. There are obviously families of objects that deserve lots of follow-up, and some that it would be really nice to know demographically that those are there. But this is a hard problem. Yet we've been working on that in my group in particular with my former postdoc, Joey Richards. We basically took the ACES survey and the OGLE survey, and we had some ground truth from work that people had done in the past. And you set aside a fraction of the data and you build a classifier on it, and then you apply it to another fraction of it, and then you set aside another fraction, you apply it to another fraction. You wind up building a notion of what's called a confusion matrix, and this is the result of that. Basically, you'd like to see all the power in the diagonal element because you're trying to predict the true class given the known class, which is all the letters at the top. And I think there's something like 25 different stellar variability classes here, not all of them periodic. What's interesting here is obviously you see some off-diagonal power, which is not so good. But a lot of the power that exists in these sort of large classes all sort of stay within those classes. That is to say, our classifier might not be good at deciding between a certain type of eclipsing binary, but it will recognize effectively that it is a multi-star system. So the state of the art from our group, and there's another group that's been working on this as well in Geneva, started getting to about 15% error rates on a sort of 26 class system, which is pretty good. Again, it's sort of noisy data, and the training set itself isn't perfect. But what's interesting is when you start taking the taxonomy into account, you wind up getting very small gross misclassification errors. So what you really care about is sort of pulsating and eruptive and multi-star systems. You can do incredibly well. So there's kind of a large amount of work in applying existing machine learning approaches to, for instance, doing machine learning on taxonometric trees in the context of astronomy to see how far we can push down this error. But some interesting things have come up while we've done this. We started thinking about how we can take the results of this learning process and apply it to a new survey. Again, it's great that I can tell you, boy, if I had had this classifier working when ACES was working, which is an old survey of essentially the whole sky, down to very sort of shallow limits, I could have done this, and this science. That's not very satisfying. What you want to do is say, well, because I've learned all this about these surveys, now when a new survey comes online, how do I sort of bootstrap into some deep understanding from day one using what I've had before? But this is problematic, and it's sort of shown in this slide here. On the left-hand side, I've got 3 different classes of stars, and I've got one feature. One of them may be period, another might be amplitude. And I can build a perfect classifier on that data that distinguishes those 3. So it's essentially a bunch of if-then statements. But if I apply that same set of if-then statements to a set of data from another survey, these are different stars, different brightnesses, you notice that my classifier is now really bad. And that's in part because the noise properties are different of the sources that I'm looking at, but it's also because I'm observing the data differently. And so the sort of changes from survey to survey are actually pretty fundamental and break our notion of what we understood in this survey as we transfer it over to the other survey. So we've been working on something called active learning, which harkens back a bit to what the last talk, or the previous talk, was mentioning, of getting people involved in sort of training classifiers. And this is where you wind up sort of asking experts to weigh in on this large dimensional feature space to get ground truth in places where there's not a lot of ground truth, so that when you build up another iteration of your classifier, you wind up doing much better. This whole thing is called active learning, and again, it's been a pretty rich place for us to work. Getting people involved, doing a spectroscopic survey to get ground truth. These are expensive endeavors. Again, from a resource perspective, but you wind up noticing that it does and improves the classifier a whole lot just with a couple of different training steps. I won't go into the details of this, but with just a couple active iteration steps, we've been able to improve classifiers markedly just by getting only order hundreds of new pieces of ground truth in a very large survey. But what it's allowed us to do is now apply our classifier to new data sets, and in this case we were able to apply it to a set of 50,000 variable stars, and we were able to more or less build up a probabilistic classifier, which I'll tell you about in a second. I will say just, and you've seen this slide already from the previous talks, on Galaxy Zoo, what we did in PTF is asked a whole bunch of people to weigh in and discover supernovae, but we used their results and their statements about explosive things in the sky to train a classifier. And on the same data, we were able to essentially outpredict the people that we had learned from. And that's a very interesting thing where you can basically have what are called noisy labels at a very high rate and still build a very good and very robust classifier. And so it was sort of this moment and realizing that we could put the results of this new classifier into practice, they were able to basically build a surrogate of what the supernova zoo people would say about a new incoming object. And as you heard, that part of that of the zoo were able to shut down, and we were able to repurpose those people for other things. So this is an example not just of having experts in the loop, but having sort of the crowd help us and build a better and better classifier. Okay. I want to go back just to some of the, I guess these are the outcroppings or the natural exhaust of having done these large-scale machine learning exercises on variable stars. Classification probabilities wind up reflecting in the end kind of, in some sense, the ground truth of whether something really is a type 1a supernova or a type 1b supernova. There is obviously no obvious, absolute ground truth, but eventually we'll end up getting a spectrum and we'll be able to put it in a bucket definitively. What's really interesting is that now we can sort of emit probabilistic catalogs that people can decide what they want to do with it. And I think this is one of the things that we're going to have to deal with in the big data era, is that catalogs of transients and variable stars have to become probabilistic. There is no such thing as this thing is a type 1a supernova or this is an R. Lyrae. It's this with this level of confidence. So we built a website for those that want to see it. You can go and kind of explore these 50,000 stars and look at the different class probabilities in the context of this taxonomy. And then each individual star has its sort of own page associated with it. And you can look at an individual star and its classification. Here we're looking at ones whose top probability is an R. Lyrae pulsating in the fundamental overtone mode. You see a light curve there. And then you see the classification vector on the right-hand side over there. We try to make it social so that Facebook might buy us or something. I don't know. Anyway, check it out, bigmac.info, probabilistic catalog. Doing science with probabilistic catalogs is pretty interesting. If you're looking to do demographics, you want a sort of high purity sample, but you don't mind missing a whole bunch of things, low efficiency. And then novelty discovery is also critical. And we've been able to do that and actually find some very rare types of objects using the survey and using the catalog we built. So last, I'll just sort of end with another statement about now the sort of the online practice of doing classification. What we had for a number of years within PTF is essentially a robot which wasn't just doing discovery, but also starting to make some inferences before any people were actually looking at the data. In the end, this is an event that turned out to be pretty interesting. It was in Nature a couple of weeks ago. And so in the end, we had to have people sort of writing that paper and deciding why this was interesting, but the robot got it right. It was a transient, and then it realized with a little more data, it was actually a supernova, and then it got all the follow-up after that. So I guess just sort of end with a couple of challenges that I see of using machine learning in the big data era. And basically just kind of read these off. How do we formally imbue our domain knowledge and knowledge of physics into the process of machine learning? And there, doing sort of feature engineering is going to be important. The cold start bootstrapping problem is going to be a significant one for LSST, I believe. From the machine learning perspective, the noisy and dirty and irregularly sampled data is actually quite interesting for them. But making decisions with incomplete data is also a very interesting one, too, in the context of resources. How do I know when I need to stop observing something when I know, even though I haven't reached my inference, that there's a high probability that that inference would remain the same if I acquired another data point? And I think critically is how do we actually teach people to use this toolkit effectively to get ML, to get the ML sort of derived results understood and accepted in the community. And last, on the kind of parting thoughts, I hope you've seen that astronomy's deluge really requires us to change the traditional roles that astronomers have had, at least in the time domain loop. And yet there's still some really critical pieces of that loop that are important for people to be involved in, not necessarily in the real-time part of it, but in the learning part of it and the relearning part. What's also, I think, important to note is that deterministic predictions with verifiable uncertainties is absolutely critical and crucial to maximize scientific impact under real-world resource constraints. And that is to say, if we can't come up with probabilistic statements, then we don't really know how to take action on them. If I call everything an RLIRE and everything else a type 1a supernova, I'm going to blow away all my Keck time, right, for follow-up. So we have to figure out a way to put error bars on everything. And in that sense, when I make a prediction about what something is, and then it leads to actual using resources effectively and efficiently, that's really the gateway to understanding. So the connection back to what industry is doing of mostly doing prediction, and we're really involved in understanding, I would argue that prediction is the gateway to that understanding, because really to do things well, you need more resources. And I guess last, I'll just point out the original slide I showed you. And for those that didn't realize, Henrietta Swan-Leavitt is in the back there. And she's having her green peas moment where she's doing something she wasn't told to do. She's actually discovering a fundamental relation of how pulsational variables vary in their period and how they're related to their luminosity. She was tasked with looking at stars that were in double systems. And instead, she wound up realizing something very interesting about the data that she wasn't asked to. So despite all the maybe pessimism you might have about the fact we're replacing people in that entire stack, that top level of inference and aha and eureka moment, I think, has been there from the beginning in astronomy and is never really going to go away. So I'm with that.
So classifiers usually assume that the object you're looking at is something you've already seen before. Whereas, in these new very large data sets, the hope is, that you're going to find something you haven't seen before. So can you just talk a little bit? I mean, do you just look for things that have low probability of to all the fits, or are there ways to somehow try to optimize for discovery of genuinely new stuff?
Yeah, so we've started to take a stab at that. And we had an undergraduate looking at an existing survey that we classified. And then what we try to do is we try to build clusters in spaces that were far away from known clusters. And again, you're doing this in a large dimensional space, so it's a non-trivial exercise to do right in a statistically sound way. And she found a new cluster, and we got very excited. And we started looking at those light curves, and it was basically these flat light curves, and basically this huge bump up that went up for a couple of months and back down, and didn't do anything, and then came back again about a year later. And there were a whole bunch of those. And then we started thinking about, wow, we've just found a new class of object. This is pretty cool. Then you actually look at the data, and you realize these are mirror variables that are in crowded fields, and the size of the aperture from that survey was so large that you were basically capturing the DC level of the background, and when the mirror got fainter, you didn't see it anymore, and it just would rise above. So there's at least some level of indication that new things can be found like that. The other approach, and that's really sort of an unsupervised approach, a more supervised approach, would be to simulate light curves of things that you think you might be looking for, like parent stability supernovae or kilonovae, which maybe there's an example of that already, and simulate families of those, and then basically simulate what those would look like and make sure that your classifier is capable of finding these. But you'd have to really start from the physics, I think, to do that. To find an anomaly in real time that looks nothing like anything else, you could basically just ask, as I think you were intuiting, what class does this new thing belong to? And if they don't belong to anything at some level of threshold, then maybe you throw that into an anomaly bin and you follow it up.